where are the aliens? Given that our star and Earth are part of a fairly young planetary system compared to the rest of the universe, and that it's possible for a civilization to achieve interstellar travel during this time, it seems we should have been visited by some form of extraterrestrial intelligence by now. Now, some say it's not a real paradox, because we can only guess that there is intelligent life out there. But the Drake equation is used in this so-called paradox to estimate the number of possible civilizations in our galaxy. The Drake equation uses 7 variables to estimate the number of detectable civilizations in the Milky Way. This gave us an idea that there could be millions of Earth-like worlds with civilizations out there. But this was back in 1961, and no one knew of any worlds orbiting stars other than our own. It was only recently that we got a good idea. In 2020, astronomers using data from the Kepler Space Telescope found there are more than 300 million worlds with similar conditions to Earth scattered throughout the Milky Way. The analysis concluded that roughly half of the galaxy's sun-like stars host rocky planets in habitable zones where liquid water could be on the surface. In fact, planets are extremely common and outnumber all the stars in our galaxy. And very soon, the James Webb Space Telescope will be headed into space to look for new potentially habitable worlds. We'll have a new video on that soon, so make sure to stay tuned here. Now that we know how many worlds there are and how many possibilities that there could be advanced civilizations, the question remains, why is the universe silent? Maybe we're about to find out soon as technology advances, or perhaps we've already been visited by some faraway civilization and just don't know it yet. There have been many unexplained UFO sightings recently, and some believe extraterrestrials are already here. Solid proof of that would put an end to this paradox. The bootstrap paradox is a paradox of time travel that questions how something that's taken from the future and placed in the past could ever come into existence in the first place. It's a common theme used by writers inspiring plot lines in many science fiction films, such as the Bill and Ted movies, Terminator, and Doctor Who. So let's look at one of the examples of this paradox. Imagine that you're a time traveler, but before you go on an excellent adventure, you go into a bookstore and buy a copy of Hamlet, written by Shakespeare. You then travel back in time to London during the Elizabethan era and give the book to Shakespeare. William S. then copies the book and claims it as his own work. Centuries go by, and during this time, Hamlet is printed and reproduced countless times until a copy of it ends up in the same bookstore that you bought it from. The question then becomes, who wrote Hamlet? This is another famous paradox, which involves you going back in time to take out your grandfather. By that we mean erasing his existence. Now, we know everyone here loves their grandparents, but this is only an example. Once again, you're a time traveler, and you pop back in time to do the deed and erase your grandfather's existence. You then return to present time. But the thing is, with your grandfather gone, your father wasn't born, and you now realize you never even existed. Everything about you has now been erased, including all your family, friends, all your possessions, and your history. So you wouldn't have been born in the first place. So it would be impossible to do this. Now, some scientists believe that if this were to happen, you would have now created an alternate timeline or even entered a parallel universe. By the way, for those who missed our video on parallel universes, check out the link in the description. Another interesting variant to the grandfather paradox, going back in time to eliminate Hitler to stop World War II. This would have some interesting consequences. Let's say you have a shiny time machine, and you've got a plan to go back before things get out of control during the war and put things right. The problem now is that the action removes any reason to travel back in time, along with any knowledge that the reason to time travel back ever existed. Acting as a time-traveling executioner simply creates a paradox, and along with the many worlds idea, traveling back in time might create a new timeline without Der Führer. But the old timeline would also still exist. You might even create a new timeline that's even worse. But what would happen if you sent something back through a wormhole? The red sky paradox. Among all the stars in the Milky Way, 80% are red dwarfs or M-type stars that, according to scientists' calculations, may continue burning for trillions of years. To compare, the Sun will burn for about 5 billion years, so it's not surprising there are now more red dwarf stars than any other. With so many red dwarfs out there, our night sky should be dominated by their light, and at least some of them should host planets suitable for living organisms. So where are all the red dwarfs, and why haven't we found life in their systems yet? This is the red sky paradox, proposed by astronomer David Kipping from Columbia University. The way we view stars in space is different from what we would see through the Earth's atmosphere. From space, the Sun appears white, massive hot stars appear bluish, and cooler stars appear either white or orange. Red dwarfs are so dim that even the nearest star, Proxima Centauri, cannot be seen with the naked eye. In telescope images, such stars can have different colors depending on the filters used. But the red sky paradox has nothing to do with the color of the universe, but with the search for alien life. The idea is that planets in red dwarf systems have the best chance of developing life. Such stars live longer, and there are a lot of them. About 15% of red stars have Earth-sized rocky planets orbiting them, and most of these exoplanets are located really close to their stars, so they have plenty of light and heat, which also means there could be liquid water on these planets. And yet, life as we know it only thrives on Earth, which orbits a yellow dwarf. But yellow dwarfs make up for just a few % of the stars in our galaxy. So does this mean our star is special? Well, not exactly. The Copernican principle states that there are no privileged or special regions in the universe. In other words, our place in the universe is ordinary, but that doesn't mean life is ordinary throughout the universe. But there may be some answer to this so-called paradox. Red dwarfs might be more dangerous to surrounding planets by flooding them with deadly radiation. When these stars' gravitational forces are so strong, nearby planets are tidally locked to their star, turning one side into a red-hot hell, while the opposite side is cold and icy. Planets in red dwarf systems also lack protection from objects coming from space. Open the NASA catalog and look for gas giants near red dwarf stars. They are extremely rare, and giants like Jupiter often serve as a sort of space defense in a star system. They interact with comets, asteroids, and other celestial bodies that can destroy or severely damage rocky planets. All this, according to Kipping, makes life 100 times less likely to occur in red dwarf systems than in yellow dwarf systems. Space is full of interesting stars, and one of them threatens to disrupt the accepted picture of the universe. The late, great Joseph Polchinski is the famous theoretical physicist who wrote the book on string theory. But Polchinski also came up with a potentially paradoxical situation involving a billiard ball sent through a wormhole that travels back in time. In this scenario, the billiard ball is fired into a wormhole at such an angle, if it continues along the path, it will exit the wormhole in the past at the right angle to collide with its earlier self, thereby knocking it off course and preventing it from entering the wormhole in the first place. However, some physics students came up with solutions which avoid any inconsistencies by having the ball emerge from the future at a different angle than the one used to generate the paradox, and deliver its younger self a glancing blow instead of knocking it completely away from the wormhole. A blow which changes its trajectory in the right way, so that it will travel back in time with the angle required to deliver its younger self this glancing blow. Now here's something that will make you think about reality differently. The paradox of the oldest star. The star named HD 140283 is located in the constellation of Libra, about 190 light-years from Earth. Astronomers first determined the age of the Methuselah star when they used the Hipparcos telescope to measure its speed. They found the star moves 1.3 million kilometers per hour. But what surprised astronomers the most was the star's age, which was estimated to be about 16 billion years old. The result seemed very strange to scientists, given the age of the universe itself is only 13.8 billion years old. So they decided to dig deeper. After 8 years, and with the help of the Hubble telescope, astronomers conducted studies by parallax, spectroscopy, photometry, and star luminescence. They concluded that HD 140283, according to new calculations, is 14.5 billion years old. But because it's extremely hard to precisely measure the star's distance and brightness, there's an uncertainty of 800 million years to its age. That is, the star may well be 13.7 billion years old, meaning younger than the universe, although not by much. But what about the star that's much closer to us? The observer's paradox is something very strange indeed. And of all the bizarre facts of quantum theory, there are fewer stranger than Schrödinger's famous fable about a cat that's neither alive nor deceased. For the record, this is a thought experiment only, and no animals have ever been harmed. The paradox describes a cat that's locked inside of a windowless box, along with some radioactive material, a Geiger counter, a hammer, and a container of deadly poison. The radioactive material has a 50% chance to decay. If the Geiger counter records an emitted radioactive particle, it then triggers a hammer that smashes a vial of poison that will be fatal to the cat. However, you would not know if the cat was alive or deceased until you opened the box. And so until the box was opened, the cat would be both alive and deceased at the same time. How is this possible, you ask? This is because simply looking at matter actually changes the outcome of what happens to it. You can't know something is there unless you see it. Now, you're probably saying this whole thing is very strange, but consider another observer's paradox called the double slit experiment. This is the most famous physics experiment of all time. Imagine a wall with two slits in it, and then throwing tennis balls at the wall. Some of them will bounce off the wall, but some of them will travel through the slits. If there is a wall behind the first one with slits, some of the tennis balls that made it through will hit it. Now, if you mark where the tennis balls hit the second wall, you should expect to see two strips of marks, roughly the same size as the slits. Sounds pretty straightforward. But in the double-slit experiment, something awfully strange happens when you shine a light through the slits. Light isn't just a wave, it's also a particle called a photon. Now, if you shoot a single photon at the double slits, it forms an interference pattern on the back wall, as if it's interfering with itself. It's like the photon went through both slits at the same time. But this is where it gets stranger. Simply by looking at the double-slit experiment, the behavior of the photons changes, as if the photons are alive and know you're watching them. We know this because if the experimenter tries to find out which slit the photon is going through, the interference pattern doesn't show up at all. The bottom line is that observing a photon can change events that have already happened. How is that possible? No one's figured it out yet. Maybe you might be the one to solve this puzzle. The faint young sun paradox. According to the standard model of stellar evolution, 4 billion years ago, the sun emitted about 30% less energy than it does today. With less energy reaching the planet, astronomers say that the Earth should have been frozen solid during these early times. But some scientists think this isn't what happened. According to the climate models of the Earth, during the Archean Eon, 4,000 to 2,500 million years ago, the climate was about as warm and humid as it is now. There was no ice at the poles. Single-celled prokaryotes floating in bodies of water produced oxygen, which would later ensure the evolution of all life on the planet. Obviously, both of these scenarios contradict each other. Scientists say the planet stayed warm during this era, but how did it manage to do so? The heat could have come from the Earth's crust, which was still cooling after the planet was formed and gravitationally compressed. It's also likely that the heat was retained after a collision with a protoplanet, presumably the size of Mars. As a result, the Moon was created. Early tides between the Earth and Moon were very powerful. Because of this, the Moon became tidally locked in just 100 million years of its formation. Tidal heating could have raised the surface temperature of the early Earth and triggered volcanoes around the planet. Emissions of gases into the atmosphere as a result of such events created a powerful greenhouse effect. Most likely, carbon dioxide and methane were the main contributors. In addition, there were almost no clouds in the Archean sky. They usually form when sunlight evaporates water, but there was very little light and thus very few clouds. But the rare clouds reflected a minimum of the star's radiation into space. Enormous amounts of methane could have covered the sky with a thin photochemical haze, dyeing the clouds pink. This stunning show lasted until about the end of the Archean Eon. Then, because of the increasing concentration of oxygen in the atmosphere, methane oxidized, and the clouds took on their familiar snow-white appearance. You've heard a lot of strange things happening in the universe, but strange things are also happening around our Milky Way galaxy. One of the biggest paradoxes in physics is the black hole information paradox, a puzzle that results from the combination of quantum mechanics and general relativity. Calculations show that physical information could permanently disappear into a black hole, allowing physical states to devolve into the same state. But this is controversial because quantum mechanics states that information can never be destroyed. Let's say you burned 2 different letters written on paper. Putting them back together from ash would be nearly impossible, but not entirely. The small differences in smoke temperature and the amount of ash would still retain information about the 2 different letters. The problem with black holes is they suck things up and then, over a very, very long time, radiate what they've swallowed back out in the form of Hawking radiation. Unfortunately, unlike the smoke, temperature, and ash from burning a letter, Hawking radiation contains no information about what the black hole ate. This is because all Hawking radiation is the same, which implies that black holes destroy information about the universe. So, do evaporating black holes really destroy information, or does information escape as the black hole evaporates? A new generation of physicists say that information does indeed escape a black hole by their radiation, and they've identified an invisible surface that lies inside a black hole's event horizon called the quantum extremal surface. This surface appears to encode the amount of information that's radiated away from the black hole, evolving over the black hole's lifetime exactly as expected if information escapes. Apparently, something can escape a black hole. The paradox of missing dwarf galaxies. According to the standard model of cosmology, large galaxies should have hundreds or even thousands of dwarf satellite galaxies around them, but so far only 30 have been found around the Milky Way. This is roughly 1% of the predicted number. So where are the missing dwarf galaxies? One idea is that at some point in evolution, bigger galaxies could have captured these tiny galaxies by their gravity, or it could have been the result of some cosmic catastrophe. But perhaps we just haven't been able to track them all. More often than not, they're incredibly small and dim. Some contain only a few thousand stars. Meanwhile, the Milky Way holds 100 to 400 billion stars. With the brilliance of its stars, it outshines the modest reflections of tiny galaxies. But the paradox of the missing Milky Way ultra-faint dwarf galaxies doesn't end there. These mini-galaxies challenge the entire Newtonian model of gravity. The thing is, their rotation is odd. In the cosmological model, satellite galaxies should be formed as individual objects before being captured by larger galaxies. And because they would be coming from different directions, they couldn't be arranged in a disk-like structure. But the 11 brightest dwarf galaxies are distributed exactly like that, and all galaxies rotate around the Milky Way in the same direction. This is somewhat similar to the way planets of our solar system orbit the Sun. According to scientists, such a layout could only be explained if gravity was stronger than predicted by Newton. And that's where the paradox arises. Scientists suggest dark matter clumps in these tiny galaxies aren't big enough to attract gas and form stars at all. So that would make them invisible to us. But it's dark matter that binds space objects together by its gravity, and there has to be a lot of it. Astronomers at Cambridge University have studied about 7,000 galaxies and found there's 400 times more dark matter there than usual matter. However, in May 2022, astronomers at the University of Barcelona in Spain announced the possible discovery of 11 galaxies devoid of dark matter. Inside dark matter galaxies, stars must move much faster than Newton's theory of gravity predicts. So if the data suggested by the Spanish astronomers is confirmed, Newton's theory will have to be modified. This won't be the first time the fundamental principles of physics have to be changed. And this always leads to major shifts in the way we see the universe. We've created the internet, landed on the moon, discovered the Higgs boson, and our spacecraft have entered interstellar space. It seems that in the past 100 years, we've accomplished more than we could ever think of, and it's difficult to imagine that we could go any further. But what if that's just the tip of an iceberg? What if all human progress is nothing but our collective illusion? Over time, the Kardashev scale of a civilization's technological advancement has expanded and narrowed. One of the ideas is that there are 4 levels of civilizations in the Kardashev scale. Type 1 civilization, or a planetary civilization, would be capable of harvesting all the energy resources available on its planet. Type 2 civilization, or a stellar civilization, would go further, being able to harness the energy of an entire star, basically allowing it to control a whole planetary system. A Type 3 civilization, or a galactic civilization, could utilize the energy resources of an entire galaxy, move planets, and feed black holes with stars. But even that's far from what a Type 4 civilization would be capable of, creating a universe itself. And according to this scale, we haven't reached Type 1 civilization status, but we're not a Type 0 civilization anymore. So, where does this leave us then? 0 on this scale signifies a specific amount of energy consumed by a civilization, which is roughly 1 megawatt of power. Currently, our average annual energy consumption is roughly 17.7 terawatts. And just a single terawatt would be enough to power 10 billion 100-watt light bulbs simultaneously. Human beings have a score of about 0.73 on the Kardashev scale. But how fast can we reach the milestone of Type 1 civilization? One famous theoretical physicist has estimated that if we increase energy consumption by 3% yearly, it would take 100 to 200 years to get there. As for now, about 1 billionth of our star's energy reaches Earth, and we only use 1 millionth of that. Once we achieve this status, we'd be able to utilize all the sunlight, wind, and tides available to us. Weather conditions would be controlled by our will, and we'd be able to alter the course of earthquakes and volcanoes and make floating cities on the water. All this sounds like we'd have superpowers, but that's nothing compared to what civilizations of Type 2 is capable of. Also called a stellar civilization, it would go far beyond harnessing energy from its home planet. At this level, intellectual creatures could control their entire parent star's energy output, and there are several ways to do it. One idea is to use a megastructure called a Dyson sphere. Its simplified version, a Dyson ring, would consist of a bunch of solar power collectors encircling a star at, for example, about 160 million kilometers. And as this civilization continues to advance its technologies, it would add more rings around a star, each having its own orbit. Eventually, this megastructure, the size of our planet's orbit around the Sun, would resemble some type of a shell encompassing a star, blocking most of its light, but also collecting most of its energy. For us, the creation of such a technology would mean nearly the same as the invention of electricity. Starlifting is yet another method to steal some energy from a star. But how exactly does it work? A highly intelligent civilization midway to Type 3 civilization would possibly know how to siphon material from a star and put it into a spinning black hole's ergosphere. The ergosphere is a region surrounding a black hole outside its event horizon, and lots of fascinating phenomena happen there. By sending material into this region around a black hole, you could get energy back out at much higher speeds. This is called the Penrose process, and according to this, roughly 29% of the energy in a black hole could be extracted. But there's also a downside to this method. A black hole will start spinning slower and eventually it will stop. However, this also opens another possibility: harnessing Hawking radiation from evaporating black holes, which is far beyond our capabilities. But it would hardly be rocket science for a Type 3 civilization. This galactic-level civilization would essentially use the same technology as a previous one, but at much, much larger scales. We're talking galactic scales. Entire galaxies would be filled with Dyson spheres surrounding billions of stars. New planetary systems would be artificially made. Their supplies of energy would be infinite. They would practically become immortal. And the only thing that would threaten their existence would be a sudden natural catastrophe, such as the massive explosion of a supernova. For humans, at least 100,000 years are needed to become as advanced. And it could even take 1 million years to become a Type 3 civilization if we ever survive long enough. But do such civilizations exist? And if so, such an intense technological activity would be easily observable in space. According to NASA, we found about 4,000 planets outside our solar system in the past 2 decades. And in the Milky Way alone, there should be trillions of stars accompanied by planets. So why haven't we found any signs yet? This is called the Fermi paradox, and it says that our universe is too old and too large for there not to even be a single other life except for the one we have on Earth. But throughout decades, we haven't found anything like that. But we may not have looked hard enough. The ongoing search for extraterrestrial intelligence is limited to catching several frequencies of radio and TV emissions. The problem is, such signals could only be made by a Type 0 civilization. And because they also interfere with static charges in space, a good portion of that signal is lost. A much more effective way would be to break signals into all frequencies to preserve most of that signal. Sadly, a hypothetical Type 0 civilization using only one frequency wouldn't be able to read that message fully, hearing nonsense instead. So even if the Milky Way is loaded with a variety of messages from Type 2 or Type 3 civilizations, human Type 0 radio telescopes cannot hear them properly. Another researcher at the National Astronomical Observatory of China came up with a new theory of where those civilizations could be hiding. A professor and her team scanned a significant portion of the sky and detected 21 galaxies. They were searching for unusual radio signals to detect alien exhaust, and the 2 weird galaxies they've discovered had enhanced infrared emissions that couldn't be explained by natural phenomena. Astronomers hope it could point to a bunch of Dyson spheres and entire galaxies captured by an intelligent civilization or civilizations. But to prove the idea, they need to know for sure what's causing these infrared emissions. There's also another solution to the Fermi paradox. Perhaps these civilizations have decided to stay unnoticed. Our universe is vast, and just because we haven't succeeded in finding anyone doesn't mean they're not there. When looking for signs of technologically advanced civilization, astronomers often base their observations on different types of infrared emissions and waste. But what if a super-intelligent civilization has not only come up with unimaginable technologies, but also found a way to hide its presence? If so, all this time, we've been searching for something we shouldn't and neglected what demands our utmost attention. If we continuously fail at finding any signs of extraterrestrial civilization, we could try studying what's missing instead. Because the most likely scenario is if a Type 3 civilization existed somewhere out there, it would gather all the energy available in a galaxy and exhaust all its power supply, leaving nothing behind. And there are such empty regions in space, the Great Voids, which were once believed to be signatures of intelligent life, but this theory was refuted. And although scientists haven't lost hope, most of their studies eventually come to a dead end. And if that's always the case, there arises another question. What if we just came to be at the wrong time? According to one computer simulation, intelligent life could have been more abundant 4 billion years ago than at any other moment. It may seem unbelievable, but if primitive life existed on Earth roughly 3.5 billion years ago, why couldn't intelligent life exist elsewhere in the universe at about the same time? And should we even try so hard to satisfy our natural curiosity with the threat of possible extermination of human beings as a species? We all come from one ancestor, and we cannot restrain our anger towards each other. So, should we think that a hyper-advanced civilization would care more for our lives than we do? Today we're scared of exhausting our planet's resources. Type 2 civilization would be afraid of the death of their star, and Type 3 civilizations would be concerned about how to escape the death of the universe. But if we look at the broader version of the Kardashev scale, for a Type 4 or even Type 5 civilization, even that wouldn't be something to worry about. These creatures could theoretically form a new universe. And according to one physicist, the energy needed to give birth to a baby universe in a laboratory would require about 1,000 trillion degrees, which is far below the limit of such a civilization's capabilities. Although Type 4 civilization is hardly ever achievable, it would literally mean becoming the creators of everything we could ever observe, think, or imagine. Given how fast we evolve, and that even today the creation of effective tiny laser-propelled spacecraft are within our arm's reach, it could be true that we've already been visited in the past, and the odds of noticing their presence almost equal 0. Even now, we may be observed by a much more advanced civilization that just waits till we make enough progress to eventually get in contact. Or maybe they've already decided to reach out, but it will take hundreds of thousands of years till they arrive here from another galaxy at the other corner of the universe. But even if we don't find anybody, it doesn't necessarily mean a bad thing. Sure, we would feel lonely and maybe even abandoned, but this would also mean that we have the chance to set the foundation for the future stages of human evolution. One day, those hyper-intelligent creatures, somewhat resembling us in appearance, could think of us as pioneers, explorers, blindly discovering this dark place we were put in as a child discovers the world. Maybe it's all our imagination that makes us think they exist, and maybe they do. But it's not them, it's us. Future us. Superhuman beings. You may have heard the term Fermi paradox before. In its simplest form, the term asks the question, if intelligent life is common in the universe, then where is everybody? You might be thinking that the physicist Fermi wrote papers on the subject, and that his life work was based around finding aliens. But this couldn't be further from the truth. Enrico Fermi was a physicist who created the world's first prototype nuclear reactor. He never really wrote much about extraterrestrials. Fermi was chatting with colleagues at a lunch in Los Alamos about a cartoon showing aliens emerging from a flying saucer carrying trash cans stolen from New York City. That's when Fermi asked, "Where is everybody?" Everyone understood he was referring to the fact that there wasn't any solid evidence of alien visits to our big blue planet. The conversation then turned to the topic of interstellar travel, where Fermi concluded interstellar flight might not be possible, might not be worth the effort, or a technological civilization doesn't last long enough to invent interstellar travel. Keep in mind that Fermi was studying this in 1950. When rockets hadn't yet reached Earth's orbit. The so-called Fermi paradox, which questions the existence of extraterrestrial civilizations, actually misrepresents Fermi's views. Fermi didn't question the possibility of alien civilizations, only their ability to have interstellar travel. So what is the Fermi paradox if Fermi didn't create it? In 1975, an astronomer by the name of Michael Hart penned an article in which he said, "They are not here, therefore they do not exist." Hart's claim was that if smart aliens existed, they would inevitably colonize the Milky Way. He believed that if they were anywhere, they would be here by now. But since they aren't, and we've seen no signs of aliens, it means that humans are the only intelligent life in our galaxy. And if that's the case, then looking for intelligent life elsewhere is probably a waste of time and money. But then another famous physicist named Frank Tipler came along in 1980 and elaborated on Hart's assessment and asked the big question: where would a civilization get the resources needed to colonize 1 billion stars? He came up with an interesting idea where a civilization could build an artificially intelligent machine comparable to the current human level that could replicate itself. If you sent one of these out to a neighboring star and told it to build copies of itself using local materials in that system, then you could send those copies out to another neighboring star until the galaxy would be crawling with these self-replicating machines. Tipler said that since we haven't seen any of these machines, that we're the only intelligent civilization in the galaxy. Now, we really have no idea how many advanced alien civilizations might be out there that could pull off such a feat, but a man by the name of Frank Drake came up with an equation that gives us a rough estimate of the number of civilizations in our galaxy that might have signals we could detect, and those civilizations could exist in the thousands. Many different solutions to the Fermi paradox have been suggested over the years. One solution to the so-called Fermi paradox might be the scariest solution of them all. It's called the dark forest theory, written by Chinese science fiction writer Lai Cixin. And it's possibly the most chilling theory, as you'll soon find out. Imagine the universe as a vast dark forest, and us humans, along with other advanced civilizations out there, are the hunters. The hunter doesn't light a torch to draw attention to himself. To be noticed might be harmless, but on the other hand, it could bring the jaws of a hungry lion, or even worse, get the attention of another competing hunter. Now, we don't have interstellar travel yet, but as far as interstellar communication, it's possible with technologies and equipment that's already available. Lasers could easily send signals across the galaxy. Of course, there could be delays in the signal, assuming the limitations of the speed of light. But we've done a lot more than just send out some radio signals. In fact, we've done everything but be silent, from deliberately sending messages and spacecraft out into space, to unintentionally sending out radio and TV signals which leak into space. The Voyager probes are already on their way out of the solar system, and if there is intelligent civilization out there, they could be intercepted. These two probes basically carry all of humanity with them. That could be a good thing, or it could be a bad thing. That said, we've more than lit the torch in the dark forest. The next question is who or what will spot our signal and come back to check it out. This should make everyone nervous. Famous science fiction writer Arthur C. Clarke once said that two possibilities exist. Either we're alone in the universe, or we're not. Both are equally terrifying. We should understand that it's impossible to know the intentions of a newly contacted civilization if one was ever found. It could be possible that some alien civilization could have studied us, seen our destructive nature, and decided it's better to leave us alone. We could end up wiping ourselves off the planet, let alone worrying if someone will do this to us. We could end up being lucky, and a more advanced civilization would step in to help us reach the stars and become an interplanetary species by sharing their technology with us. There might be peace on Earth after the realization of not being alone in the universe. But we need to be realistic and ask ourselves, why would another civilization do this? Another advanced civilization out there might be scared to death of what we could do to them if they were discovered. On the other hand, it might be in civilization's best interests to shoot first and ask questions later to avoid being destroyed or wiped out by another more advanced civilization, as we've seen in several science fiction films like War of the Worlds. Nobody knows who would annihilate who in the first meeting. It's pretty much a given that if a civilization has discovered interstellar travel, their weapons technology is likely far more advanced than anything we have here on Earth. That's what the dark forest theory is. That it's possible all other civilizations out there in the cosmos have chosen to remain silent for fear of being destroyed. But the scariest thing about this remains, and there's nothing we can do about it now. We've just been too noisy. It could be that there are many different extraterrestrial civilizations out there that know we exist. But the reason we don't know about them yet is because they haven't been transmitting signals like we've been doing from Earth. An intelligent civilization out there that's discovered Earth might not see us as a threat to them, since we haven't reached a technological level for interstellar space travel. But they could be waiting for that moment. They could be waiting to see if we will continue to be a peaceful race, or if our planet will just become uninhabitable to all life anyway. However, it would be really tough for another advanced civilization to stop accidentally sending out radio signals into space like we do, unless they're more advanced and use another form of communication that we cannot see, hear, or understand. And that brings us to another possibility as to why we don't see or hear anything from space. Maybe there really isn't anyone out there. That's pretty hard to believe, since there are as many as 40 billion Earth-sized planets in habitable zones. But despite the fact that the universe may be teeming with hospitable planets, there's no guarantee they'll stay that way long enough for life to evolve. According to a recent study from Australian National University, wet, rocky planets like Earth are very unstable when they're first formed. If any kind of alien life hopes to evolve and thrive on a Terran planet, there's a very limited window of just a few 100 million years to get everything moving. Think about our own planet and what it's been through. From a ball of lava being pummeled by asteroids to a freezing ball of ice and then back again. The chances for life to succeed on an initially wet, rocky planet in the habitable zone is extremely difficult. It's not that life might be rare or hard to get started in the universe, but the habitable environments aren't stable during the first billion years. Of course, thanks to our Earth, here we are. We know from our own discoveries that the universe is a deadly place. All it takes is a supernova, a gamma ray burst, a solar flare, or a huge asteroid to wipe out life on a planet. We know some of those things have happened right here on Earth. It might be difficult to deal with the fact that we're the only intelligent life in the Milky Way, or perhaps the entire universe. Perhaps after all these billions of years, other civilizations have come and are now long gone. And maybe we're the last ones left in the universe. As for the Fermi paradox, there really isn't one. We can't say that aliens exist or not because no one knows if travel between star systems is possible in the first place. There was a lot of excitement when the Central Intelligence Agency declassified thousands of UFO documents. In some of those 3 million documents, there was not enough evidence to identify objects caught on aircraft instruments. Maybe extraterrestrials are here now, and we just don't know about them. Regardless of whether we have or haven't been visited by extraterrestrials in our galaxy, UFO experts say that humanity is closer than ever to finding the existence of alien life. With all the telescopes we have searching, we're bound to find something. So what do you think? Do you think we'll find evidence of life out there sometime soon? And should we keep looking for aliens? Astrophysicists are trying to figure out what destroys entire galaxies in the most extreme regions of the universe. Scientists at the International Centre for Radio Astronomy Research in Australia have studied more than 11,000 galaxies and concluded that their gas and dust are being stripped away. Without this building material, galaxies stop forming new stars, and the old ones eventually fade away. So what's causing galaxies to be eaten up by some unknown galactic monster? And what cosmic anomalies still defy explanation? One idea is that this is caused by the increasing expansion of our universe. So speed may just be as dangerous in space as it is on the road. When galaxies start moving too fast in their cluster, storms can arise within them, capable of rapidly pushing gas out of galaxies. But there are other possible ideas. Black holes are thought to be located at the center of most galaxies, and because of the strong radiation of matter inside these black holes, powerful particle streams burst out of them. These cosmic jets can blow everything out of a galaxy. Another possibility is that galaxies are digging their own graves. They start burning up stars much faster than their neighbors and don't have time to recover their gas reserves. This leads to their slow extinction, which scientists call strangulation. Whatever the reason behind this mass destruction is, scientists struggle to understand the existence of some galaxies. These are red-hot Jupiters, huge gas planets similar to our Jupiter that orbit in the arms of their stars, and scientists don't understand how it's possible for their existence in the first place. But there are 3 hypotheses. The magnetic field of a parent star could be a protective barrier for a gas giant, or the red line for a planet is its dust disk. A gap is formed between the inner edge of such a disk and a star, neutralizing the attraction of that star. Alternatively, a planet's approach to a star stops when the elongated orbit of a hot Jupiter transforms into a circular orbit. While scientists look for evidence to back up their theories, giant worlds keep surprising researchers. Take WASP 121b in the constellation Puppis, for example. Lying 850 light-years away from Earth, the planet is 1.74 times the radius of Jupiter and 1.157 times its mass. The giant rotates so close to its star that it makes an orbit around it in just 30 hours. That's 68 times faster than Mercury rotates around the Sun. Particles of molten iron, magnesium, chromium, vanadium, aluminium, and titanium create clouds on the cooler hemisphere of WASP 121b. There, aluminium condenses with oxygen, and together with admixtures of chromium, iron, titanium, or vanadium, Its droplets form either rubies or sapphires, which might fall like rain on the planet. However, no alien life would be able to make use of these gems because of the proximity to its star. WASP 121b is about 2,700 degrees Celsius, making the existence of protein life there impossible. Although the majority of objects in the universe come to an end in a quiet extinction, some of them stop existing in a more impressive manner. Back in 1967, the Vela satellite, designed to monitor secret Soviet nuclear tests, detected a blinding flash of gamma rays outside the solar system. Gamma rays are a very powerful kind of electromagnetic radiation, and astronomers observe approximately 1 gamma ray burst per day in distant galaxies. These flashes in space happen as a result of some of the strongest and brightest explosions in the universe. Their duration can range from 10 milliseconds to several hours. When something like this happens, sometimes the amount of energy released is about as much as our sun radiates in 10 billion years. Astronomers were able to identify stars that turn everything around them to dust during such events. Prolonged gamma-ray bursts occur during hypernovae or the death of a star with more than 30 solar masses. Sometimes an explosion can be 100 times more powerful than a conventional supernova. And these dead stars leave behind giant rotating black holes. Short-lived gamma-ray bursts are also believed to be caused by neutron stars. As a result of a ripple in space, a neutron star can collide with another neutron star or be swallowed by a black hole. The nature of such events is still not fully understood. Recent observations have shown that after gamma-ray bursts take place, all photons travel in the same direction. Then, suddenly, at some point in space, they inexplicably change their path. It's also strange that gamma-ray bursts have energy focused in a narrow beam, so our satellites don't see many of them. Astronomers estimate that there may be actually about 500 gamma-ray bursts happening every day. Scientists believe the LIGO Observatory, Laser Interferometer Gravitational Wave Observatory, which is very sensitive to gravitational waves, will be able to record many more gamma-ray bursts. Let's hope that they don't find gamma-ray bursts anywhere near the Milky Way. One of them was earlier observed near our galaxy about 450 million years ago, and it caused an ice age on Earth, which ended with the Ordovician extinction, one of the 5 largest in the history of the planet. A new flash nearby Earth would presumably destroy the ozone layer of our planet. If this happens, all life will cease to exist as a result of the deadly ultraviolet radiation. However, because there are no neutron stars in the vicinity of the Milky Way, as well as candidates for supernovae or hypernovae, scientists are confident that the probability of such an event is close to 0. There definitely will be other dangers discovered to our solar system and to our planet in the future. But for now, it doesn't look like we have anything to worry about, except for the occasional asteroid that flies by our planet, sometimes unexpectedly. Most galaxies are structured with filaments of gas and dust between stars, or a type of cosmic skeleton that appears to hold everything together. A few seconds after the Big Bang, dark matter and dark energy spread throughout space. A kind of web was formed, and dark matter seems to be responsible for the large-scale structure of the universe as we know it. But wait, what is this stuff we're talking about? Dark matter is thought to be a non-luminous material that makes up around 27% of the universe, and could take the shape of many different forms of particles, including weakly interacting particles or randomly moving high-energy particles. Dark energy, on the other hand, is an unknown form of energy thought to make up roughly 68% of the universe. Researchers found evidence of dark energy by measuring supernovas, which showed that the universe doesn't expand at a constant rate, but is actually accelerating. In simpler terms, dark matter is like glue or cement that seems to be holding the universe and everything in it together. And dark energy is the force that's pulling on the universe in every direction and accelerating its expansion. So what's so special about this? Take a look at this image of the galaxy NGC 1052 DF2 from the constellation Cetus, which is located 62 million light-years away from Earth. At first glance, there's nothing special about the image, except this galaxy has many fewer stars than the Milky Way. But this isn't what really got scientists' attention. The galaxy, along with its neighbor galaxy NGC 1052 DF4, seems to be missing all dark matter. The largest map of the universe's dark matter was made by astronomers at the observatory in Chile and demonstrates this phenomenon. So why is there no dark matter in the galaxies from the constellation Cetus, and how do these two galaxies manage to survive and not fall apart? One suggestion is that larger neighboring galaxies have stripped gas from galaxies DF2 and DF4. Now they're tearing apart their smaller neighbors. And in the latest study, cosmologists have suggested that about 8 billion years ago, two dwarf galaxies collided with each other. The cosmic catastrophe resulted in a distribution of gas which formed many new dwarf galaxies. Eventually, the two newborn galaxies didn't get dark matter, so they now have to survive without a skeleton. But this is not everything that has astronomers baffled. More than 400 exoplanets discovered by scientists shouldn't have survived either. We usually think of gravity as a force between objects with mass. It's easy to see how this force works by stepping on a scale to see how much you weigh. The number on the scale represents the Earth's gravity on your mass, or your weight on planet Earth. When it comes to gravity in the cosmos, we can imagine the Sun's gravity keeping the planets in their orbits, and we all know about the strong gravitational pull near a black hole. The so-called force of gravity is easy to understand, and gravity might seem like a simple thing after all. But things are different in the current age, as we know now that gravity as a force is only a small part of a more complex phenomenon thanks to the general theory of relativity. But before we get into that, it's time for a little Physics 101. Everyone is familiar with Newton, who was a veritable demigod of physics during his time, and the story about the apple falling on his head. Well, that didn't really happen. The truth is, Newton saw an apple fall from a tree and was in a contemplative mood. At that moment, he wondered why the apple fell straight towards the ground, and not sideways or in another direction. He presumed that a force of gravity between two bodies pulled them towards each other with a magnitude directly proportional to their mass, and also inversely proportional to the square of the distance between them. The path that the bodies take will be the shortest to minimize energy use, therefore a straight line. In short, Newton believed an apple falls because a gravitational force accelerates it towards the ground. Newton probably thought there was something missing from his theory though, because it said he wasn't completely satisfied with it. This is because he originally thought of the force of gravity as a push, not a pull. Little did Newton know that he was partially right about this, but his theory of gravity was accepted as gospel, that the magical pull was an essential property of mass, the theory which withstood and obscured the truth for the next 400 years. That was until Albert Einstein, another formidable genius, came along in 1905 and presented his general theory of relativity while working as a Swiss patent clerk. His challenge to Isaac Newton's theory was either ridiculed or ignored completely because his ideas seemed too radical to be possible. The key to understanding the theory of general relativity is that everything in a gravitational field falls at the same rate. But it wasn't Einstein that figured this out. It was Galileo that first concluded that all objects released together in the absence of an atmosphere will fall at the same rate regardless of their mass. A famous experiment by Apollo 15 astronaut David Scott was done on the moon to test this theory. At the same time, moonwalker astronaut Scott dropped a hammer and a feather, and they both glide to the ground and impact the ground at the same time. The same thing would happen for any object regardless of its mass or its physical makeup. This is known as the equivalence principle. So why do the two objects fall together and land at the same time? It's because they're not falling. They're standing still, and there is no force acting on them. With Einstein's theory, gravity is not a force between two objects with mass. Instead, gravity is the warping of space and time in the presence of objects with mass, and without some force acting upon the objects, they will travel in a straight line. Einstein believed smaller objects are not pulled on by more massive objects, but instead the objects are being pushed down by the space above them, and that there is no such thing as a gravitational force. According to Einstein's theory, matter warps not only the fabric of space, but time as well. This is called space-time, and any object in space warps this space-time continuum. Space-time is the three dimensions of space: length, width, and height, combined with the fourth dimension, time. The more massive the object, the more it warps the space around it. Einstein believed that apples fall from trees and planets orbit stars because the objects are moving along curves in the space-time continuum, those curves being gravity. A good example to see how this works is to visualize the Earth on a grid of space-time. You can see the mass of the Earth warps space-time and creates a kind of gravity well. Any object around this mass, you, me, and even the moon, is pulled down and towards this gravity well. The moon also warps space-time with its mass, but the gravitational field between the Earth and the moon is not strong enough to pull the moon towards us. Instead, it's also like an apple falling from a tree. The sun also has a huge gravity well that keeps everything in our solar system from flying off into space. We can also understand how gravity wells around planets in our solar system work by how we've launched spacecraft. To get spacecraft moving in different directions from their launch path and increase their speed, engineers used warped space-time, or the gravity around other planets in our solar system, to get a gravitational slingshot that sends the spacecraft in another direction with greater speed. The closer to the planet, and therefore its gravity well, the faster the object will begin to move. What it all comes down to is that objects in the universe are attracted to each other because space-time is bent and curved. The closer they are to the object of mass, the faster they will accelerate. But what about this so-called gravitational field we were talking about earlier? Is it not a force? A gravitational field is actually the force field that exists in space around every object with mass. The Moon has a smaller gravitational field than the planet because of its mass. The Earth has a much stronger gravitational field over the Moon because of its mass. But in space, a gravitational field exists almost everywhere. With everything floating in space above our heads, it might be easy to believe there is no gravitational field at work in orbit around our big blue planet. However, even the International Space Station feels the gravity of Earth. The surprising thing is, the effective gravity in orbit around the planet is nearly the same as the one on the surface of the planet. In fact, it's about 90% as much in orbit as on the surface of the planet. So if you weighed 100 kilograms on Earth and had a space ladder that reached all the way to the space station, you'd weigh about 90 kilograms up there. But wait a minute. If there is gravity in space around the planet, why do astronauts look like they're floating around in zero gravity? The reason astronauts look like they're floating in space is because everything, including the International Space Station, is falling together at the same time in the vacuum of space. This condition, in which it appears people and objects are weightless, is called microgravity. If everything falls in the same way regardless of its mass, then a free-floating astronaut far from any gravitational source and a free-falling astronaut in the gravitational field of a massive body would each have the same experience. In fact, the space station, satellites, and everything else up there is always falling towards the Earth. And while the International Space Station is falling, it's also moving very fast, at about 28,000 kilometers per hour from the pull of the Earth's gravitational force. There are some ways to prove Einstein is right about objects with mass warping the fabric of the universe called space-time. The gravitational acceleration at the Earth's surface is 9.81 meters per second. The reason gravity pulls you and other objects towards the ground has nothing to do with the core of the planet. All objects with mass bend and curve space-time, and that curvature of space is gravity itself. So if you were to somehow make a journey to the center of the planet, there would be no gravity. You would be away from the curvature of space-time at the center of an object with mass, and therefore floating around the core of the planet weightless. But as you started to make your way back to the surface, you'd start to feel the curvature of space-time from the mass of the Earth, and the effect of that curve, gravity, would start to get stronger. Of course, we'll have to get a probe to journey to the center of the Earth to nail that one down. But there is another way to prove that gravity warps space-time. One of these things is called gravitational lensing. This happens when a massive celestial body causes a big enough curvature of space-time that the light around the object appears visibly bent, as if you were looking at a camera lens. This gravitational lensing happens when the massive object, such as a galaxy, warps the space around it into rings of light. Interestingly enough, this has helped us find other galaxies and objects in space that we wouldn't otherwise see without the gravitational lensing effect. Einstein's cross is a famous example and shows a gravitationally lensed quasar that sits directly behind the center of a galaxy. 4 images of quasar appear in the foreground due to the strong gravitational lensing of the galaxy in the middle. It might seem like Einstein has this whole gravity thing locked down. and there is a lot of evidence to support general relativity. But here's the big problem. In its current form, it's incompatible with quantum mechanics. Quantum gravity is theoretical physics that seeks to describe gravity according to quantum mechanics. As of now, there's no such theory that is universally accepted and confirmed by experience. But that's not all. Researchers understand that at some point in a black hole, Einstein's theory breaks down and stops working. Scientists used 3 giant telescopes in Hawaii to watch a blue star called SO2 make its closest approach to the black hole Sagittarius A star in the middle of the Milky Way galaxy in its 16-year orbit. If Einstein's theory was right, the black hole would warp space-time and extend the wavelength of the light from the star. The waves of light would stretch out as the intense gravity of the black hole would drain their energy and cause the light from the star to shift from blue to red. And just as Einstein predicted, the star began to glow red. Had it been another color, it would have hinted at a completely different model of gravity altogether. Right now, scientists are looking for a curvature of space-time that is so extreme, the theory of general relativity fails. They believe that in the next 10 years, the theory of general relativity will be pushed to its limits, and another genius will come along and show us where Einstein was wrong. Let's hope we don't need to wait another 300 years. In 1994, it looked like the Hubble telescope captured an object depicting a beautiful city with snow-white towers floating in space. People called it Heaven or Celestial City. Believers of alien civilizations were excited and even speculated the city was actually the center of our universe. But after a careful examination, astronomers declared the image fake. Scientists later explained the Hubble image captured was galaxy NGC 3079. Part of this image was cut out, photoshopped, and a celestial heaven was ready to trick the world. And even though there's nothing mysterious in the image, it has fueled widespread interest in the structure of our universe. So, does the universe have a center? And how do we find out if it exists? Since ancient times, the sky dotted with the lights of stars has intrigued people, and they wanted to know if there was a center to this boundless cosmic canvas. Our ancestors associated it with something earthly and familiar, like flowers. Egyptians considered the sky as a lotus and its core as the center of the universe, where gods dwell. Later, the ancient Greek philosopher Aristotle came to the conclusion that the planets and even the sun revolve around Earth. And in the 16th century, Nicholas Copernicus was convinced the Earth itself revolved around the sun, which was thought to be the center of the universe. In the 20th century, more advanced telescopes revealed how vast the cosmos is. At the beginning of the century, the American astronomer Harlow Shapley made a map of the Milky Way. According to it, the Sun is just one of 100 billion stars in the dark corner of our galaxy's spiral arm. And in 1929, the American astronomer Edwin Hubble proved there are thousands of galaxies in the universe and that ours isn't unique. Today, our planet's cosmic address is very long. The Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Laniakea Supercluster, Universe. This alone shows how complex and immeasurably diverse the structure of the universe is. Everything in the universe spins, from small asteroids to entire galaxies. But does the universe also spin? If it's possible to figure this out, we can calculate its center, a fixed point on a spinning object. Our planet's center of rotation is the axis connecting the north and south poles. For a basketball player spinning a ball on his finger, the center of rotation is the point of his finger's contact with the ball. But it seems that the universe has no such point. All our observations show that unlike stars, planets, and galaxies, it doesn't rotate. And this means it's impossible to find its center in a conventional way. But maybe we can find it by mass. If an object has an end, it has to have a beginning, and its center would be a point that, on average, has the same mass in all directions. However, according to the standard model of cosmology, the universe is isotropic. It's the same everywhere. Of course, the mass of galaxies differs in some of its areas, but on average, it'll be the same in huge regions of the universe, millions of kilometers in size. The cosmos is like a cellular sponge, only an extremely large one. And it doesn't matter whether you're looking at this mega sponge from Earth or from the most distant exoplanet ever discovered. The picture won't change much. The problem of finding the center of mass in an homogeneous space is impossible. Nonetheless, another component of the cosmological model, the expansion of the universe, may provide a clue. In 1929, Edward Hubble measured the speed of galaxies located at different distances away from our planet. Hubble noticed galaxies are flying away in all different directions from Earth and are accelerating in speed. And because of that, we can assume they all started moving from the same place. In ordinary life, finding the point of expansion of an object is easy. Screw a rubber sheet to the ground and then ask your friends to pull it from all sides. You'll notice that the point where the sheet is attached is the center of its expansion. But then the same can apply to the universe, right? Since astronomers can see the expansion of galaxies from Earth, then our planet should be a kind of center too. Well, the process of our universe's expansion works differently. Scientists have found that galaxies fly away when observed from any point in space, not just from Earth. The farther away from the observer, the faster galaxies move away from them. So how does this work? According to Edwin Hubble's calculation, called the Hubble constant, galaxies recede away from each other at the speed of 70.4 kilometers per second per megaparsec, or 3.26 million light-years. At 1 billion light-years away, the expansion of the universe is carrying galaxies away from us at 22,000 kilometers per second, or about 7% of the speed of light. But at 100 million light-years away, this speed is only 2,200 kilometers per second. So when looking at galaxies from different places in the universe, hypothetical civilizations would see galaxies moving away slower or faster, depending on where they are. And because of that, we cannot find a center of the universe in such a way. But couldn't we measure it from the point of the Big Bang? We believe the universe was born about 14 billion years ago in the Big Bang, a massive cosmological explosion or expansion. We know that after any explosion, material expands from a specific point. It's sometimes possible to calculate such a point even with the naked eye. For example, if you take a picture of fireworks and look at the direction of light flying in the sky, it's easy to figure out where the fireworks burst out from. Does this mean we can apply this method to the Big Bang? Cosmologists believe we cannot, And not just because of the immense scale of the event, but also because it occurred when space and time didn't exist. The Big Bang happened everywhere in the universe all at once. Only then did matter begin to spread randomly throughout space. We know this because of relic radiation that emerged after the Big Bang. This is called cosmic microwave radiation, which permeates space in all directions. Its approximate temperature is 2.7 Kelvin, but in some regions it can be colder. In cosmic voids, the temperature of relic radiation is a fraction of a degree lower. But no deviations from the average temperature have been found in larger regions of space. And if the Big Bang did have an epicenter, it would have been much hotter closer to the epicenter than elsewhere. Scientists compare the universe expanding after the Big Bang with a two-dimensional ball with points drawn on its surface that symbolize galaxies. If we inflate the ball from the inside, it'll grow in all directions equally, and it won't have a specific center. The dots on it will become evenly distant from each other, but the problem with this comparison is the universe must have an end. But what if the universe is infinite? Scientists are finding more and more evidence for this idea. And if this is the case, we'll never be able to determine the true size of the universe, and because of it, its center. Accelerating faster and faster relative to the observer, at some point, the expansion must exceed the speed of light. And when this happens, we would find ourselves surrounded by an event horizon we wouldn't be able to look beyond. But what about the electric charge of the universe? Would it help us to find a center? Modern science tells us that the distribution of the charge of the universe is, on average, homogeneous. There are equal numbers of objects with negative and positive charges in huge regions of space. And as a result, the total electric charge of the universe is zero. So we won't be able to detect any special point in this way either. So far, everything indicates the universe has no center. And of course, it does not rotate. However, an international team of astronomers claim they might be able to pinpoint a center of our universe with the help of the so-called dark flow. Scientists made this hypothesis after studying galactic clusters from data collected by the Wilkinson Microwave Anisotropy Probe. They noticed that about 1,400 galaxies between the Sales and Centaurus constellations behave abnormally. Unlike others that travel rather randomly, these cosmic objects move in the same direction. According to astrophysicists, galaxy clusters are gravitationally attracted by something with an extreme mass. This force drives the dark flow through the whole observable part of the universe and even beyond its limits. And it does so with an insane speed, not less than 600 kilometers per second. Cosmologists suggest that this flow gradually pulls in more and more galactic clusters, and their point of attraction could be the center of the universe. Scientists believe that this could be a black hole, and if so, it's so huge it has no analogues in the known universe. Perhaps the black hole is preparing for a new Big Bang. For this to happen, it would need to pull in and compress all the matter and energy of the universe into an indivisible singularity point. An interesting idea is that through the center of this black hole, our universe could flow directly into some parallel world. When we sleep, we can hardly distinguish reality from a dream. So how do we know what's real and what's not? To scientists, something is real if its properties are determined prior to being measured. An apple can be green even when no one is looking at it. But the quantum world seems to be following different rules. And 3 scientists have recently won a Nobel Prize proving our universe isn't locally real. But if our world isn't real, what is this place we live in? Imagine there are 2 people, Anna and Luke, both located on opposite sides of our solar system. 2 coins are sent from the center of the solar system, each targeted towards one observer. While the coins are moving through space, they're spinning. According to quantum mechanics, it's impossible to predict which side the coins would land on. The results are random, but when Anna measures heads, she instantly knows Luke's coin should have landed on tails. The odds of correctly predicting this even 200 times in a row are 1 in 10 to the 60, which is more than all the atoms in the solar system. Even though Anna and Luke are separated by billions of kilometers, quantum mechanics says Anna can keep predicting Luke's results based on what she got, as though the coins had a kind of telepathic connection. This thought experiment is known as the Einstein-Podolsky-Rosen paradox. It seems impossible, and yet this is how the universe works. How can something travel faster than light? What is the pixel of our reality? And how does the universe change from predictable to random? Before quantum mechanics, scientists believed that the world was deterministic. They thought that if they knew certain properties about a physical system, they could determine everything about this system in the past and the future. But then, physicists discovered a phenomenon called quantum entanglement that describes a state in which 2 particles stay connected regardless of how far apart they are. This may not sound too exciting, but imagine this works even if the entangled pair is on opposite sides of the universe. This seems odd, even in the world of quantum mechanics. We generally believe that nothing can travel faster than light, meaning there's a limit to how fast any signal can travel. However, if you create an entangled pair of particles and send them from the opposite direction, increasing the distance between them, and then measure the quantum state of one particle, the quantum state of the other particle will suddenly be determined. You can imagine it as 2 boxes, each containing either a white or black stone. So whenever and wherever a person opens one of the boxes, they immediately know the stone in the other box. This has been demonstrated across distances of hundreds of kilometers over time intervals of less than 100 nanoseconds. 1 nanosecond is equal to 1 billionth of a second. So, if the 2 entangled particles somehow exchange information, they do it at speeds at least thousands of times faster than light. But that's not all. Just like we stand on scales to measure our weight, scientists measure particles to discover their properties. But what if those properties only became determined the moment you measure them? This would mean our universe couldn't be both local and real. At least one, if not both, of these premises would be wrong. Defining reality is a tricky thing to do. We don't see tiny particles, yet they exist. We cannot touch the air, yet it is there. So what is real? In physics, real means that objects always have definite properties, regardless of whether we are measuring them or not. In other words, a falling tree in a forest makes a sound even if there's nobody there to hear it. And local means that objects can only be influenced by their surroundings, and that this influence cannot travel faster than light. It's important that our world is real because, as Isaac Newton believed, if you know the positions and velocities of all ingredients of our world, and you identify the forces that influence them, physics can predict what the world would be at any time in the future. But the quantum world often has indeterminate nature. Put simply, it's often random or cannot be predicted. Consider a simple experiment. Fill a container with several radioactive atoms and wait. Generally, it can be predicted how many atoms will remain and how many will decay. However, you can never know for sure which atoms will and won't survive. Or fire a number of particles through a narrowly spaced double slit. You can predict what interference pattern will appear on the screen behind the slit, but you'll never know where every individual particle will land, even if they are being fired one at a time. Some aspects of quantum physics appear to be completely random. But are they really random? What if we just lack information? Albert Einstein believed that entanglement wasn't violating local realism, but rather that quantum physics was incomplete. He thought that the variables connecting these entangled particles would eventually be found. And the three scientists, John Clauser, Alan Aspect, and Anton Zeilinger, shared a Nobel Prize for proving these hidden variables don't exist. The scientists have reached a conclusion that an entangled particle doesn't have any properties until somebody measures it, and so these properties cannot be known or guessed by any means. So if the universe isn't real, then exactly what are we seeing and experiencing? A group of physicists in Los Angeles have come up with a new theory of reality, and it's based on periodic patterns or crystals. Crystals can be of different shapes, but also of different dimensions. Even more so, a higher dimensional crystal can be projected to create a pattern in a lower dimension. The resulting pattern is called a quasi-crystal. Physicists took a specific 8D crystal, projected it to 4D at a certain angle. From it, they have driven a 3D quasi-crystal, which they believe is a substructure of all reality. The fundamental building block of this 3D quasi-crystal is called a tetrahedron, or a three-dimensional triangle, with all its sides of the same length. And this length is the smallest theorized unit of length in existence, called the Planck length, which is 10 to the minus 20 times the size of a proton. If an atom was the size of the Earth, a Planck length would be about the size of a proton. This is where it gets spooky. According to their theory, just like digital displays consist of the smallest units of a digital image, pixels, a tetrahedron is a 3D pixel of our reality. Each tetrahedron has just a few states in which it can exist, and the state of one tetrahedron defines the state of other tetrahedrons that fill the entire space of the universe. But if a tetrahedron can only be in one specific state in a given moment, who or what dictates the state it should be in? Physicists all across the globe believe that reality is made of information. But what is information? Information is meaning expressed through symbols, but meaning is nothing else but comparison or an ability to perceive something relative to something else. And if so, comparison and meaning require choice. In other words, consciousness. So just like when we know what the properties of an entangled particle are when we measure them, meaning or information can only exist when it's perceived or measured. If all of this is true, reality could be a product of consciousness. But there's also another idea for our existence. The simulation hypothesis, suggested by the Oxford philosopher Nick Bostrom. And some scientists believe the odds we live in a simulated reality are 50-50. So, if we were somehow able to prove we're living in a simulation, how would we do it? We'd have to start with the idea that the hardware which created the simulation doesn't have infinite computing power, because otherwise it wouldn't be possible to distinguish our reality from a virtually created one. Put differently, we wouldn't be able to notice any glitches. So scientists are looking for ways to make a simulation reveal itself with experiments that would create an overload on a theoretical computer with finite computing resources. Meanwhile, other scientists are finding other proofs. All computing hardware leaves an artifact of its existence inside the simulated reality it is running. So there should be a limit to the processing speed of operation per certain amount of time. And it happens that we have such an artifact in our universe, the speed of light, which remains the same regardless of the observer. It has an upper limit, and it cannot be explained by physics. So we may not know what kind of a computer is running our simulated reality or what properties it has. But there's one thing we can say for sure. If it performed one operation per second, its memory container size for the variable space would be roughly 300,000 kilometers. Perhaps we have this light speed limit because otherwise we would be able to travel to another galaxy before this computer could program it. But it's not the only indication we might be living inside a simulation. Movies or video games often go into the point of view of characters to demonstrate things from their perspective. What we see on the screen and hear from the speakers is the integrated experience that serves no purpose for characters. It's there purely for our benefit. And so if we accept the simulation hypothesis as our new reality, consciousness obtains a clear purpose. It's an integrated subjective interface that consists of 5 senses. No natural laws, philosophical or scientific ideas predict the emergence of consciousness, and there's no clear utility or evolutionary advantage that it could provide. So it seems its primary function is for there to be an experience. But since experience without any clear utility or evolutionary advantage is so energy expensive, it must serve someone else, an observer or a player. If one day we discover a way to simulate conscious beings, the chances we're living in a simulated reality would skyrocket. Physicists at the University of Maryland have already been able to simulate a single nucleus of helium that is composed of 2 protons and 2 neutrons. And they think that if they manage to simulate an atomic nucleus today, perhaps in 20 or 30 years, they would simulate a molecule, and in 50 years, an object the size of a few inches. If the progress continues, it's possible that 100 years from now, scientists could simulate the human brain. The thing is that if we are really living in a simulation, we aren't programmed to do things because we have free will. Perhaps someone wanted to see what we would do without any instructions, and what would happen. Perhaps the long years we experience in our reality would only be minutes to the creator of the simulation that we're in. However, to give a game character its own consciousness is something far beyond any technology that we currently possess. So what do you believe? Is the universe and everything not what it seems? Are we living in a simulation? We want to hear what you think. So sound off in the comments. And thanks for watching.